Hey guys, this is Mr. Gilbert coming to you from my garage. Darn weather's not cooperating with outside lectures today. I hope everyone is well. As always, if you need anything, don't be afraid to reach out. Whether that's help with science work or something else, or even if you need something more important like food or whatever, make sure you reach out to me or the school. We're willing to help out. The scheduling material is still on the website, so make sure you've done your scheduling. And then again, just make sure you're doing those Friday checkpoints so I know who's doing their work. We're going to look at wave interactions today. How do waves interact with other things in their environment plus other waves? So there are really three main things we'll be looking at. There's reflection, refraction, and diffraction. Reflection, refraction, diffraction, and then looking at wave interference as well, and a couple of other terms that come along with that. So we'll start with reflection. Reflection. So if I have a surface, we'll just make a wall here. So that can be a mirror or just any flat surface that it's bouncing off of. And so a light wave comes in, or a sound wave or whatever, is going to come in and hit this. This angle is called the angle of incidence. I'm going to put an I there. Whatever that angle is, that's the angle of incidence. And the wave is going to bounce back off at this angle. And this is going to be the angle of reflection, R. I, the angle of incidence, is always going to equal to R, the angle of reflection. That is called the law of reflection. So whatever angle it comes in at is the angle it bounces off at. The angle of incidence equals the angle of reflection. All right, those are always going to be equal. Law of reflection, angle of incidence is equal to the law of reflection. Now there are weird situations where we have a bumpy surface. All right, so we have a bumpy surface, and let's say this comes in and hits here. Well, that's going to reflect back here. And the angle of incidence and angle of reflection are still the same, but you're going to end up with this. It's called diffuse reflection. That's diffuse reflection. Diffuse reflection is where you have a rough surface, and so it's going to make this distorted image. That doesn't mean the law of reflection is not true. What it means is it's bumping, so this one's going to go back that way. But the next wave down, if you look where the hump is, just below that light wave coming in, the next one's going to go downward, and so it makes this distorted image or distorted sound. Like if you picture really rough walls and bad sound, bad acoustics in a room, that's diffuse reflection. And so the law of reflection is the same. It's true no matter what. Incidence equals reflection. It's just a matter of what does that surface look like that's bouncing off of. There are two terms with reflection you need to know. One is called a real image, just real image. Real, and one is a virtual image. You have real and virtual. A real image is an image that seems to pass through. An image that seems to pass through, and that comes from a curved mirror. That's when the image looks kind of funky because the mirror is not flat. It's curved. It's convex, means it's curving out towards you. If you look at the back or the bottom of a spoon, or if you look at the inside of a spoon, that's called a concave mirror. Concave. All right, and so anytime we have those situations, anytime we have those situations, we're going to get a weird image. It's called a real image. So the image is still true, but it's misshapen because of the shape of the reflecting surface or the mirror. A virtual image is on a flat mirror. A virtual image is a flat surface that's reflecting off of. And a virtual image is defined as an image that seems to be behind the mirror. So, like if you're standing there looking at a mirror, just a regular mirror in your bathroom or whatever, it looks like you're just standing on the other side of it. That's a virtual image, right? So virtual image, flat mirrors, real image, curved mirrors. And again, this applies to all waves, but light waves are the easy example. Now, there's something weird, and you can do a quick demonstration at home if you want. With a curved mirror, there's something called a focal point. So I'm going to clear my screen here. real quick, and you can do a quick demo with this at home if you want. But if I have a curved mirror, there's something called a focal point. So this reflection is going to come this way, and this reflection is going to come this way. And there's something called a focal point right here. This is a focal point. It is the point, and I'm not going to get into the complicated part of this because of it being an online lecture, but this is the focal point. At the focal point, the image flips. And so there's something kind of weird that happens. If you take a serving spoon, so if you have a big metal spoon at your house, you can do it in a little one, but it's easier to see the bigger the spoon. But if you can take a serving spoon and put it really close to your face, so put that serving spoon right here, and you'll be right side up. But if you move it back so far, your image will flip upside down. And you're like, whoa, that's really trippy. So it'll be up, right side up, and you get so far away, and the image will flip. It'll be blurry for a second, and then you'll be upside down. That point where you flip is called the focal point, right here. All right? And that is going to be the inside of the curve. So if you will picture, if your spoon were to be turned into a sphere, into a ball, it would be the middle of the ball. And that is where your image would flip upside down. And so if you want to do that at home real quick, it's kind of cool. But basically what's happening is the image is flipping because you're passing that focal point. So you should be right side up and then upside down. It's kind of neat. Right? And that's a real image. Again, it's a curved reflection. So that's called a real image. All right. One place that we see reflection used a lot would be in sonar and echolocation. Think submarines or even bats. Finding prey or finding surfaces, even when we talk about sonograms, ultrasounds, that's the same idea. Is how far away is it reflecting off of something? All right, so that's reflections. The second one's refractions, and we're all familiar with refraction. We'll define refraction as the bending of a wave as it goes from one medium to another. Refraction is the bending of a wave as it goes from one medium to another. So there are two places. So refraction. There are two places that we're used to seeing this. The first one, very simple, is in restaurants when we're drinking our water or our sweet tea. And so we have a cup. And in our cup we have this straw. With a straw or a spoon if you have sweet tea. But for some reason, it looks like our straw is like bent or broken as it moves from the glass of water to the air. It looks like our straw or our spoon is bent or broken. That's called refraction. And basically what that is the light wave that you're seeing there that is reflecting off of that spoon or straw is being bent or broken as it goes from the medium of the water or tea into the air, whereas the part of it that's already in the air isn't changing mediums. You're just looking directly at it through the air. So I can see the straw or the spoon directly in the air where my eyes are, but the part that's in the liquid is changing mediums. It's going from water or tea to air, then to my eyes. And so it looks broken or bent. All right. The other place that you often see it is if you swim a lot, if you have a swimming pool or your family does and you get to swim often, maybe you throw a penny into the water and you're going to dive in after that penny. All right. And so if you can picture you standing on the bank, all right, and then the pool's here, and you throw the penny here, and it looks like the penny's right there. You see the penny with your eyes, but for some reason, when you actually dive into the water, the penny's actually not there. It's there. It's off by this angle. And the reason that it's off is refraction. It's because it's the view that you have of the light wave reflecting off that penny. It's in the water, and then it's going to the air. And once you dive into the water, you see it directly instead of it changing mediums. And so you get what it actually looks like, where it actually is. And so both of these two things are examples that you've experienced of refraction. So diffraction, the next one. So that's reflection, refraction. Oops, sorry. me 1 second here. There we go. So we did reflection, refraction. Now let's look at diffraction. Diffraction, D-I-F-F-R-A-C-T-I-O-N. Diffraction. I'll mark it back out. Diffraction. Diffraction we'll define as the bending of a wave around a corner or around a barrier. The bending of a wave around a corner or barrier. All right. And so what happens, and sound waves are easy to use as the example. So if I have a wall here and this is going to hit it there, this wave is going to kind of reform on the other side like that. All right, that is diffraction. Now, there's an interesting phenomena. So even if we have two barriers, let's say, this is a single slit. There's a really famous experiment called the double slit experiment. So this wave hits here, and we're just going to have a new wave kind of form on the other side originating from this spot. All right, that's a single slit experiment. Now, if we do that again with two slits, it's kind of weird. But what's going to happen is you're going to start with one wave. It's going to hit this. And on the other side, you're now going to have two waves that can interact with each other. It's kind of weird. All right. And so by making two slits, we have diffraction happening twice. And we get two new waves on the other side. And now the two new waves that came from the same place are interfering with each other. All right. It's kind of crazy. So that is an example of diffraction. That's a double slit experiment. Now, I want to come back to this, and I know I'm getting a little longer in lecture today than I have been, but I want you to understand a couple things here, is that longer sound waves, so lower voices, lower frequency, lower pitch, so if you will, a man's voice, for example, is the longer wavelengths have a better chance of passing around barriers. So if I have this barrier, if I have a long wavelength, those can just pass on through. But sometimes if I have the same barrier, similar, sorry it's a little bigger, but if I have these little bitty wavelengths, the next wave can't get past. All right, and so what you'll find, it's a poor drawing, I know, but what you'll find is that a lower voice, a lower sound, can pass more barriers because the waves are longer and can get past that object, whereas a higher pitch, higher frequency voice can't get past that. And so what you'll find is if teachers are teaching directly by the door, that's different because it's going directly out. But if, let's say you had a group of teachers and they were all teaching on the opposite side from their door in their classrooms, you would be more likely to hear the male teachers' voices in the hallways than the female teachers' voices, because the male teachers' voices, which are lower, can get past that edge better. All right, so it's kind of a weird thing, but that's how that works. So those are examples of diffractions, where there's waves going around barriers. The last thing I want to talk about is interference. Interference is when two waves interact with each other. Interference when two waves interact with each other. So we have two types. We have constructive interference and destructive interference. It's pretty simple. Constructive interference is when two waves add together. So if this is the normal, and I have wave A here, and then we'll call that wave A, and change colors here, and I have wave B, and wave B goes exact same places as wave A. All the crests and troughs line up. All right, so this is wave B. The resultant wave, wave C, of them is them added together. That's constructive interference. And so those add together, kind of, if you will, they're in harmony with each other. And so they add together. That's constructive interference. Constructive interference. All right. On the other hand, you have destructive interference. And destructive interference is where two waves subtract from each other, if you will. It's just the opposite of what we just did. And so I have wave A, looks like this. Wave B, it's going to be on the other side. So the crests and troughs are opposite of each other. So it's wave B, wave A, and so the resultant wave, wave C, is going to be wave A minus wave B. That's destructive interference. And so they are canceling each other out. Destructive interference. All right? So you have constructive and destructive interference. Last couple things I would like you to note on this. There's something called a standing wave, and that is what we use for instruments. A standing wave is where we're playing like a wave on a string, where we have something vibrating at a natural frequency. So if you will, if something sounds like it's in tune, it's producing standing waves. That is a natural frequency where the number of waves on a string is perfect for that length of string or in that instrument. So that's why famous instrument makers like Stradivarius, why they make such good instruments, because of the precision of the measurements and the math they do to produce those. All right, so standing wave is a wave pattern where two equal and opposite waves continually interfere. A standing wave is a wave pattern where two equal and opposite waves continually interfere, and that makes a pretty sound for our interpretation from our ears. All right, that is a standing wave. And then the last term I want to give you, I'm going to skip over a couple of things from our normal notes here, is resonance. Resonance is an important word. So resonance is defined as a vibration of one particle at a natural frequency causing the vibration of the next. So if I play my guitar string and it's in tune, it will make the air inside the guitar vibrate and come back out at the same frequency. And so the sound you're getting is actually usually coming from the air. The string plays, vibrates the air comes out, and you hear that. All right. If you will, the whole thing of an opera singer breaking a glass, and there's a video to watch on that, but if I sing at the exact frequency that that glass can vibrate at, I can break the glass. All right. But you have to have the exact same natural frequency that glass vibrates at. If you will, that glass has a certain note. So if you've ever seen somebody take a wine glass and with water in it, or a water goblet, and play their finger around the rim and they make a sound, there's a certain sound that that glass can make. And so by singing at the exact frequency of that sound, which is usually a really high frequency, which is why we see opera singers doing that. See Harry Potter Part 3. But where that frequency is, that's the exact frequency you would have to sing at really loudly to cause that glass to vibrate and shatter. So that's called resonance, and that's what we use to make things vibrate at the same frequency in music. So I hope that helps. Let me add one quick thing as I close here. When we talk about, to go back to your notes in refraction, waves travel at different speeds in different mediums. That's important to note. And so the tighter the particles are together, the faster the wave travels, but the sooner the energy dissipates. So for instance, if I'm talking underwater in a pool, my sound waves travel really fast, but you can't hear me on the other side of the pool because the particles are so close together that by the time it gets there, it dissipates. If I'm standing, the energy gets weak. If I'm standing outside the pool and I'm talking in the air, somebody else can hear me pretty far away. The air particles are really far apart, and so it takes the waves don't travel as fast, as quickly, but the energy travels further. And so the more condensed the particles are, the faster the wave travels, but the sooner the energy is gone because it's hit so many other particles so fast. All right. That's a little bit longer lecture today, but hopefully that is easy. We've had a couple days of just watching videos, so hopefully that makes up for it. All right, guys, we'll talk to you later.